In this video, we're going to talk about something called projectile motion. And we're going to look into the different concepts that you need to know and the calculations that you're going to be able to do to solve for a projectile motion problem. Now, to start us off, let's just remember our motion equations. Here are our Suvat kinematic equations, and you can see the four different equations. We'll be using those for anything that is accelerating in its motion. Something in free fall in the vertical direction is definitely going to fall into that camp. And let's start off just by reminding ourselves how to do a free fall problem. So here's a scenario where you drop a ball from 25 meters up in the air. How much time would it take for this ball to hit the ground if it was dropped from this height? Well, we know a couple things about this problem. We know that it starts with an initial velocity of 0 meters per second. We also know that acceleration due to gravity is downward at 9.81 meters per second. If I treat down as being negative, we'll call that a negative 9.81. And then we also know the height of the ball. We know that it drops down 25 meters in this fall. And since it's going down, we've defined down as being negative, we'll call that a negative 25. If you wanted to, you could call both the displacement and the acceleration a positive and say that down is positive. You'll get the same number out at the end. We're looking for how much time it's going to take. So we're looking for the time, which means we don't need the final velocity. We can go in our list of Suvat equations and find that this is our equation that does not need final velocity. If I plug in my values, I'll notice right off the bat that u is going to be 0 regardless, so that first term always cancels out. It makes it a lot easier for us to solve for t. Plugging in our variables, looking for this unknown t, we'll find that the time is going to be 2.26 seconds. Now, this is a pretty standard free fall problem solving process. Figure out what you need to know, and then use the idea that it's going to just be dropped, so it's starting from rest, to fill in what the initial velocity is, and just go from there using the Suvat equations. Well, today we're going to add a little bit to this. Instead of just dropping it straight down, we're going to propel it a little bit horizontally. So I want you to think and make a prediction. If you were to take a ball and drop it, and right next to it take an identical ball and send it horizontally, perfectly horizontally at 10 meters per second, which ball will have more air time? How will the time that they're in the air compare between the straight down drop and the horizontal launch? Well, we don't have to just pretend. We can actually look at something that would happen. This is a great video. Doing this, it's called a shoot and drop, with a couple of billiard balls. And we'll talk about how this is set up here. So this is Alan. Does a great job with the shoot and drop. So you'll see him making some setups to make sure that everything is perfectly horizontal in this motion. So it's got that level, looking real good. And this contraption is an important one. This contraption will allow the plunger to fire a ball perfectly horizontally, while at the same time releasing this ball that is just held on there with that hole through the ball. So as the plunger goes, it will drop that ball perfectly horizontally, and at the same time, it will send this ball, so drop the ball perfectly vertically and send this ball perfectly horizontally at the same time. So if you place one on each side, we'll see what happens. That's incredibly satisfying. You can hear the clicks. They land at exactly the same time. All right, we don't need to watch him take it all down. So, which ball will have more airtime? Well, it's kind of a trick question. They fall at exactly the same time. So, why is that? How can we figure out and make sense out of this somewhat surprising conclusion? Well, if we were to take essentially a stroboscopic photograph and see at given time intervals where each of these balls are going to be, we know that they land at the same time, but every moment in that fall, they are always perfectly level horizontally. And if you were looking only in that vertical direction, they're traveling down exactly the same way. So another way that we can think about this is imagine that you drop a ball that's in free fall, and we know that it accelerates. So it gets farther and farther spacing as it falls because it's getting faster. And imagine if you just send a ball perfectly horizontally and just let it roll at a constant velocity. These are two different types of motion that we have talked about in our motion unit. Well, projectile motion is combining these two. In the vertical direction, it is undergoing free fall, and in the horizontal direction, it is continuing at a constant velocity. And how we make sense out of that is the position for the projectile is just a combination of these two. That you'll see it kind of following this parabolic arc. But horizontally, these time frames are perfectly spaced apart, whereas vertically, it follows that acceleration due to free fall. It gets farther and farther away. And we'll continue to see this, but that's where that arc comes from. So what can we do to actually do some calculations with this? Well, now let's look at a ball that instead of dropping it from 25 meters, we are going to launch it at 10 meters per second horizontally. We just saw in that billiard ball example, remember Alan, that something that's dropped falls exactly the same time as something that's launched. So this 10 meter per second initial velocity isn't going to change how much time it's in the air. We already solved for what if we just dropped it. So we can use that information. First, imagine that we just dropped it. We already solved for the time. We said that the time was 2.26 seconds. Cool. That's going to be useful to us because we know from this that horizontally it's moving at a constant velocity the whole time. And we started at 10 meters per second, so it's always going to move 10 meters per second horizontally, which means we can use our information for velocity. That's a constant velocity, not accelerating. We don't need suvat because there's no acceleration in the horizontal direction. We just say that velocity, that 10 meters per second, is the distance that it travels divided by the time. Well, we can rearrange that and say that the distance that it travels horizontally is the velocity horizontally times the time. Well, it's in the air for as long as it takes to fall. We calculated that to be 2.26 seconds. So the distance is going to be 10 meters per second times 2.26 seconds, or 22.6 meters. Again, what we did is just imagine that we dropped it, solve suvat in the vertical direction only, and then use that time to help us figure out how far would it travel horizontally, knowing that it's at a constant velocity horizontally. All right, we can do this to solve a problem from the beginning here. We can calculate how fast a spitball is moving. And it looks like I forgot to animate some things. We'll come back to that part that isn't hidden yet. So if I were to launch a spitball perfectly horizontally, let's say that I'm 1 meter away from the wall and it falls down 15 centimeters. I first want to figure out how long it takes to fall that distance. Because, again, something launched falls at the same time as something that were dropped. So we can look at the vertical direction of this and say, well, if it's perfectly horizontally, there's no vertical initial velocity. We're going to say it starts at 0. We know that it accelerates downward at negative 9.81 meters per second, and that vertically, it looks like it falls 15 centimeters, which is 0.15 meters. Going down, we'll call that a negative. We don't know what the final velocity is, and we're looking for the time. So to find the time, we can use that same equation that we did before, plugging in these values, which wasn't hidden before, we can calculate the time. The time is 0.175 seconds. Okay, how is that useful? Well, why do I need to know how long the spitball was in the air? I know that the distance between the straw and the wall is 1 meter. And if a dropped spitball would take 0.175 seconds to fall that distance, we know that it must have been in the air for that long. So I've traveled 1 meter in that time. I can calculate the velocity. It's just distance divided by time. Horizontally, there is no acceleration. I do not use suvat. So horizontal motion, 1 meter over 0.175 seconds will give us 5.71 meters per second. So again, I looked at this problem purely in the vertical direction and pretended that it was just a free fall drop problem. Use that to find the time. Use the time to find the horizontal motion using just the simple velocity equation. So we have seen a few different types of motion in one dimension. We have looked at accelerating motion. If something is in the vertical direction, it slows down as it goes up and speeds up as it comes down. Or if it's moving horizontally, it's going to go at a constant velocity. Constant velocity, we're always going to use v is equal to d over t. Vertical, we're always going to use suvat because there's acceleration there. All we are doing here is we are combining these two types of motion. A horizontal projectile is what we've been looking at. Something that is launched perfectly horizontally has components. You'll see this light blue vector is always the same. It's always going the same horizontal velocity. And the dark blue vector starts as nothing. There's no vertical velocity. And then every time we look at it, it gets faster and faster in the vertical direction. Well, these two vectors can be used to help us find what the overall velocity is. It looks something like this. So notice this red vector is just a combination of the two. So like this last one's the most dramatic. It is moving horizontally the same amount as the horizontal part of the motion, and vertically the same amount as the vertical part of the motion, and the combination gives us this angle that is a little bit longer than both of them. That's the overall velocity in that direction. And we can use vectors to help us do this. So if I say that I have a vector, a velocity that's moving at an angle, at some angle 55 degrees, and the velocity is 24 meters per second. Well, part of that velocity is in the horizontal direction. We'll call that ux for the initial x velocity. Part of that velocity is in the vertical direction. We'll call that uy. So x being horizontal, y being vertical. And we can calculate what these are going to be using SOHCAHTOA. X is connected to the angle, that's the adjacent side, so we'll use the cosine. 24 cosine 55 is going to give me 13.8, which means my velocity then in the x direction will be 13.8 meters per second. In the y direction, I use the sine because that's the opposite side. 24 sine 55 is going to give me 19.7. So the y direction is going to give me 19.7 meters per second. Okay, what can I do with that? Well, we can look at a two-dimensional projectile. What we've looked at, well, two-dimensional really is an angled projectile. What we looked at before was just this part, just the horizontal part. An angled projectile is one that you launch at an angle. It goes up, comes back down. It's going to be a little bit more involved, but not a lot more involved. The biggest difference is we need to deal with this velocity that starts at an angle. So the first thing that we'll do is we will break it up into an x and y component. So let's say we have 24 meters per second at this angle of 55 degrees. Well, we just looked at that. We said that the vertical was 19.7 meters per second and the horizontal was 13.8 meters per second. And to help us out here, we are going to only look at the first half of this problem because we know something about the top. Here, you see at the top, it is only moving horizontally. There is no vertical component. That's the point where it's just heading off at a perfect horizontal. Kind of like if you were to throw a ball up in the air. At the very highest point, there is no vertical velocity. It comes to a stop vertically. The only difference here is you gave it some horizontal components, so it's going to keep moving, just not up and down. So we can say that the y velocity, our final velocity at the top there, is 0 meters per second. Think to yourself, what would the x velocity be if we know something about this initial component? We had 24 meters per second at an angle. Well, we split it up into an x and a y, and that x is always the same throughout. There is nothing speeding it up or slowing it down in the x direction. it is independent from the y direction. So we had 13.8 meters per second, and we still have 13.8 meters per second. So in the x direction, nothing has changed. Well, to help us solve this, we're going to start by looking at the first half of this problem purely in the vertical direction. Let's imagine that instead of tossing it at an angle, we toss it straight up in the air. And we're going to use the velocity not of 24 meters per second, but of our 19.7 meters per second. That's the y, that's the vertical direction. So what do we know here? Well, we know that your initial velocity, if you threw it straight up in the air, was 19.7. We know that the final velocity, the velocity at the top of our first half of this problem, is 0 meters per second. And we know the acceleration is negative 9.81 meters per second squared. Here it's important to count that as a negative because we are saying that our initial velocity is in the positive direction. So the acceleration must be going down. That's a negative. We are going to find everything here. So say I wanted to start by finding the time. Well, we can find this time, this 2.01 seconds, using this equation, v is equal to u plus at. Plugging in the values that I know here and solving for t, this equation doesn't need s. It's pretty easy to find that t is 2.01 seconds. Now I could also find s. Now that I know the time, I could use any equation that I want as long as it has s in it. So I'm going to use this one here. This is what I would use if I didn't have the time anyway. So you could do this in any order. V squared plus u squared is equal to 2as. Plugging in what I know for those values, I can find that s is 19.8 meters. All right, what did I just find here? Well, t, the time, is the time it takes for us to go this first half. So it's the time to get all the way to the top. S, 19.8 meters, is the vertical displacement in that first half. Here you can see it starts at the bottom, it ends at the top. The y, the vertical displacement, is how high did it go. That's the total height of this launch. So what if I want to know some information in the x direction? Well, I knew that the first half of that timing was 2.01 seconds. But that wasn't to get all the way back down to the ground. That was to go to the top. So if I wanted to go to the top and then all the way back down, I would have to multiply that by 2. 2.01 times 2 is 4.02. That's my total time to go up and back down. Now the displacement, I need to use this equation again because in the x direction, we are moving at the same speed the whole time. Well, what speed is it? Go back to our triangle. We solved this triangle at the very beginning and said that the x direction, it was moving 13.8 meters per second. So now, instead of imagining that we threw the ball straight up in the air, let's imagine that we rolled the ball perfectly horizontally on the ground at a constant 13.8 meters per second. It's traveling at 13.8 the whole time for a whole time of 4.202 seconds. Plug that in. 13.8 times 4.02, we get 55.5 meters. That's how far it travels in the x direction during that projectile that was launched. All right, so let's look at this in general. If I have a projectile that goes up and back down, the first thing I need to do is solve for ux and uy. Now, that's going to be useful to me if I'm looking at only half of the problem. So let's look at just the first half. We know that in the vertical direction, acceleration is negative 9.81. That's our acceleration due to gravity. We know that the initial velocity is going to come all from the vertical initial, so uy, the component that I found at the beginning. The final velocity, the velocity here at the very top, well, that's all in the horizontal direction. We know that the horizontal velocity is all of that ux, but the vertical is just 0. So we can plug that in. V is 0 meters per second. Then we can solve for the displacement. If I want to know the height, this is the s for the first half. We'll find that total height. Now, if I wanted to find some information in the x direction, we know that the total time is just going to be 2 times whatever this, ended up being with Suvat. And we know that the displacement is just ux, what that x component of the velocity was, times the total time. So ux times 2t. Let's look at a couple generic examples, and then we'll go through one more with numbers all the way through. So if I were to tell you that you launched a baseball, there are two different angles that a baseball will actually make it all the way back down to the ground and hit the ground in the exact same spot as it did before, at a shallow angle and a steep angle. That does not mean that they will hit at the exact same time, however. So predict to yourselves, what do you think, or which baseball in this drawing would land first? Now, something like this is actually pretty straightforward, and kind of your gut is correct. If I were to trace this out and watch the journey, you can see it takes a lot longer for A to make that arc than it does for B, that more flat-lined version. B landed first. Something that's a little bit more complicated is, what if I change the scenario and look like this? Which one is going to land first now? They do not travel the same x direction. So let's see what happens. Well, the result is exactly the same, actually. B still lands first because the only thing that affects airtime is the vertical velocity. And think about that. The thing that controls how long it's in the air is how fast you're throwing in the vertical direction. If I threw something up in the air really fast, it's going to go higher. And the higher it goes, the longer it's going to take to come all the way back down. So that vertical velocity and the height ultimately affects how long it's in the air. The higher it goes, the longer the hang time. All right. As promised, let's look at one more example, and we'll fly through it, and you can look at the completed result at the end and pause as you need to see that final. So you hit a baseball at 24 degrees above the horizontal at a speed of 30 meters per second. How far does the baseball travel before it hits the ground? That's ultimately the thing I'm trying to answer for. Now, to know how far it travels, remember, we need to know how fast is it going the x direction and how long is it in the air for. So like, what's the total time? Because the distance will be its x velocity times the time it's in the air. Well, to get there, we need to do a lot of things. The first thing we need to do is that 30 meters per second not going to be useful to us. Instead, we're going to split it up into an x and a y. So the x part of that is going to be 30 times the cosine, because that's adjacent to the angle. That's 27.4. The y part is 30 times the sine of 24. That's 12.2. And at our final, here at the top of that vertical, or top of that arc, it's still going to be moving 27.4. The x direction is the same, but the y direction comes to a stop. That's 0. So let's look at our SUVAT here, this SUVAT for the first half. We know that the acceleration is still gravity, all vertical. We know that our initial velocity comes from that y component, that 12.2. We know the final velocity in the vertical direction is 0. So we are imagining that basically we're just throwing the ball up in the air at 12.2 meters per second. I want to solve for the rest here. If I wanted to find the time, v is equal to u plus at. So that's solving for time using everything but s. And I find that the time is 1.24 seconds. I don't really need it for this problem, but I'm going to find it anyway. Here's how I can find the displacement. That's 7.56 meters. So if the problem asked, how high does it go? This vertical, SUVAT, is going to help you do that. 7.56 meters is the total height of that journey. But what I really care about right now for this problem is the horizontal. How far does the ball travel horizontally before it hits the ground? And to find horizontal, I first need to find the total time. That's going to be double this 1.24. So 2.48 to get all the way back down, up and down. And then to find the total displacement, the total horizontal distance, it's the velocity times the time, where the velocity is the x velocity the whole way. So as if I roll the ball at 27.4 meters per second for that 2.48 seconds, and I find that the total distance that it travels is 68 meters. All right, that's a lot. That's a lot of things right there. So from this video, you should be able to compare the motion of an object dropped from rest and an object with an initial horizontal velocity. You should be able to calculate the airtime and speed for a horizontal projectile, so one without needing to split up into the vertical and horizontal directions to begin with. And you should be able to calculate the vertical and horizontal components, and then use that to help you calculate and compare the air times for two projectiles given their trajectories. So again, a lot of things there. We will have opportunities to circle back and look at these problems in different ways in the coming days.